January 22nd, 2026, an object named 3IATLAS is screaming through our solar system, but it defies every known law of nature. This is no mere space rock. New data from Harvard confirms a rhythmic, mechanical-like heartbeat, a rotation axis impossibly locked onto the sun, and a trajectory suggests it was sitting perfectly still at a galactic crossroad, waiting for us. This isn't a random encounter, it is a sentinel waking up. We didn't just find it, we just collided with something that has been watching us for millions of years. Our sun moves through the Milky Way at more than 200 kilometers per second, carrying planets, asteroids, and frozen debris along with it. Nearby stars follow their own trajectories, crossing, diverging, and reshaping the galactic environment. Everything moves, everything drifts. Motion is the default state of the universe, yet within this immense flow, something appears almost still. The interstellar object called 3IATLAS does not pursue the sun, nor does it spiral inward under gravitational capture. When astronomers measure its motion relative to the local standard of rest, a reference frame that averages the movement of nearby stars, 3IATLAS stands out as an anomaly. In that frame, it barely moves at all, like a buoy fixed in place while an ocean passes beneath it. The local standard of rest can be imagined as a galactic anchoring point, a way to filter out chaos and reveal what truly travels with the galaxy itself. From this perspective, the sun is fast, Earth is fast, and even distant molecular clouds are fast. 3IATLAS is not. For millions of years, it appears to have occupied nearly the same empty coordinates in space. This raises an unsettling question. Why would a natural object remain in a barren region, far from stars, heat, and gravity, instead of being scattered or captured by larger bodies? Random chance can explain many strange things, but sustaining stillness in a dynamic galaxy demands extraordinary coincidence. There is another interpretation, quieter but more disturbing. A stationary position within the local standard of rest is not meaningless. It is strategic. Any star system, any habitable zone, any emerging civilization will eventually drift past it. From such a position, observation requires no pursuit, no fuel, and no course correction. 3IATLAS did not seek out. The local standard of rest, or LSR, can be understood as a quiet dock within the Milky Way. It is not a location in space, but a reference frame defined by the average motion of nearby stars. By using the LSR, astronomers remove the random velocities of individual stars and expose the underlying flow of the galaxy. In this frame, stars largely share a common direction and speed as they orbit the galactic center. Anything that deviates strongly becomes obvious. An object that remains nearly stationary relative to the LSR is extremely unusual because it is neither gravitationally bound to a star nor rapidly traveling through interstellar space. The LSR functions as a dynamical calm lane where long-term stability is possible. For natural debris, occupying this state for millions of years is statistically improbable, which is why the LSR can be thought of as a conceptual harbor of galaxy. The idea of a motionless object in space creates a paradox. In a galaxy defined by gravity, radiation, and constant interaction, nothing should remain still for long. Natural bodies are pushed by stellar winds, heated unevenly, and twisted by asymmetric outgassing. Over time, these small forces accumulate, altering trajectories and rotations. For an interstellar object, the problem is even greater. Without a parent star, it should drift freely, carrying whatever velocity it inherited at birth. To appear nearly stationary relative to the galactic background requires either coincidence or continuous correction. Random formation does not favor balance. Stability must be maintained against countless perturbations acting over millions of years. This paradox forces a choice. Either our understanding of natural dynamics is incomplete, or the object is not behaving passively. Remaining still in a moving galaxy is not neutral. It is an active condition that demands explanation beyond chance alone. The galactic BOI hypothesis offers a different way to interpret an object that appears still. Instead of traveling from star to star, an advanced probe could be designed to wait by remaining near the local standard of rest. It minimizes relative motion and allows the galaxy to come to it. Stars, planets, and entire biospheres drift past naturally over cosmic time. In this model, the object is not a visitor, but a sentinel. Its position is chosen, not accidental. A buoy anchored in a calm current does not fight the ocean, it exploits it. From a fixed LSR coordinate, the probe gains repeated access to countless stellar systems without expending energy on propulsion. Dormancy becomes a feature, not a flaw. For millions or even billions of years, the buoy can remain inactive, shielded by inert material, waiting for specific environmental triggers. The approach of a luminous star, increased radiation, or spectral signatures of chemistry may serve as activation signals. Once awakened, the buoy does not announce itself loudly. Observation is subtle, data can be collected passively, light curves, atmospheric absorption, magnetic noise, artificial emissions. After the target system passes, the buoy returns to silence. Stillness here becomes purposeful, efficient observation. Your P, short for Yorkovsky, O'Keefe, Radzewski, Padak, arises when sunlight strikes an irregular object and is re-emitted as heat. The recoil force is tiny, but it is continuous. Over time, it changes spin rate, alters axis orientation, and can even tear an asteroid apart. For comets, the effect is amplified. Jets of sublimating ice act like uncontrolled thrusters, adding random torque on top of solar radiation. Observations show that many small bodies spin faster, tumble or fragment as a result. Stability is the exception, not the rule. To resist yorp over long periods, an object would need either perfect symmetry or active counterforces. Nature rarely provides either. When a body maintains a steady rotation despite asymmetric heating and mass loss, it contradicts expectations. Such behavior does not violate physics, but it pushes natural explanations to their limits today widely. The 7.1-hour pulse observed from the object is often described as a rotation period, but this interpretation raises problems. Natural bodies rarely maintain such clean, repeatable timing when subjected to variable heating, outgassing, and torque. Spin rates drift, periods evolve, noise accumulates, yet the signal associated with 3IATLAS repeats with remarkable regularity. If this rhythm is not purely rotational, it may represent a functional cycle. A fixed interval is ideal for calibration, data sampling, and system checks. In engineered systems, periodic modulation is a common method to encode status information. Light reflected from a surface can be deliberately varied in intensity, creating a readable pattern without emitting radio waves. A 7.1-hour cadence is slow enough to conserve energy, yet fast enough to track environmental change as a star system passes nearby. The key point is not the exact number, but the consistency. Natural processes tend to wander. Design processes tend to repeat. Interpreting the pulse as telemetry does not require exotic technology. It only requires intent. In that context, the rhythm becomes less like a heartbeat and more like a clock, quietly counting time while the galaxy moves on without ever revealing its origin or destination clearly. Active stabilization describes a system that does not merely endure external forces, but constantly measures and counteracts them. In space, maintaining orientation is difficult. Solar radiation pressure, asymmetric heating, and mass loss all introduce torque. For a natural object, these effects accumulate unchecked. For an engineered body, they trigger response. In an active stabilization model, the object continuously senses its rotational state. Small vents, mass drivers, or reflective surfaces are arranged with intention. When outgassing occurs, opposing jets fire to cancel unwanted spin. When sunlight produces uneven recoil, surfaces adjust reflectivity or angle to rebalance momentum. The result is not perfect stillness, but controlled stability within narrow limits. Such behavior requires feedback. Measurements feed a control loop that calculates correction and applies it in real time. This is the same principle used by reaction control systems on spacecraft, where millinewton forces maintain precise attitude for years. Energy demands are modest, but reliability must be extreme. Applied to an interstellar context, active stabilization explains long-term alignment without invoking unlikely symmetry. It also explains consistency under changing conditions, as distance, illumination, and activity vary. The object is not fighting physics, it is cooperating with it through control. The crucial distinction is agency. Passive bodies respond blindly. Actively stabilized systems respond purposefully. When stability persists despite strong destabilizing forces, the simplest explanation is not luck, but regulation maintained over very long timescales. of such durations, design choices outweigh chance, leaving persistent order where randomness would otherwise dominate motion and orientation control. The appearance of a reverse tail challenges intuition about gravity and comet behavior. Normally, dust and gas are pushed away from the sun by radiation pressure and the solar wind, forming a tail that points anti-solar. Gravity pulls material inward, never outward. A tail that appears oriented against expected forces demands explanation. One possibility is particle size selection. Larger grains respond weakly to radiation pressure and can momentarily trace trajectories dominated by gravity, producing apparent inversion. But such effects are transient and messy. They do not remain coherent over time. Another explanation invokes directed release. If material is expelled preferentially toward the sun, gravity will curve it back along unusual paths, creating a structured feature that mimics a reverse tail. This requires control of ejection angle, timing, and mass flow. Critically, the persistence of the feature matters. Short-lived anomalies fit natural models. Long-lived, repeatable geometry does not. Gravity is predictable, so are chaotic plumes. When observations show order where disorder is expected, assumptions must be revisited. A reverse tail does not break physics, it highlights boundary conditions. Either uncommon but natural processes align precisely, or forces are being applied deliberately to shape mass loss over a long time. The position of 3IATLAS is not only dynamically unusual, but also strategically meaningful when viewed through the lens of long-term observation. In a galaxy, not all coordinates are equal. Most regions are too sparse, too cold, or too chaotic to support effective data collection. A location near the local standard of rest where relative motion is minimized offers a unique advantage. Star systems pass by in predictable intervals. Our solar system represents such a target. It resides in a region of moderate stellar density, far from dangerous galactic cores, yet rich enough to produce planets. More importantly, it contains a long-lived habitable zone. If the goal is to observe the evolution of complex chemistry and biology, this is an ideal passage. The trajectory of 3IATLAS allows it to intersect the Earth-Sun plane during a narrow window of time. This does not require perfect precision, only sufficient proximity to measure atmospheric spectra, surface reflectivity, and technological noise. From a stationary post, distance becomes a variable, not an obstacle. Data density increases as the system approaches and fades as it departs. The concept of a galactic sentry reframes exploration. Instead of dispatching probes to individual destinations, an advanced civilization distributes fixed observation points. Each station operates autonomously, collecting local data and transmitting summaries when conditions allow. This strategy prioritizes patience over speed and coverage over contact. Within such a framework, silence is expected. There is no incentive to broadcast continuously. A mission occurs only when information crosses defined thresholds or when a reporting cycle completes. Most of the time, the station listens, reflects passively, and records. Gravitational dynamics reinforce this logic. A fixed point near the local standard of rest experiences minimal shear relative to passing systems. Orbits are predictable, encounters are gradual. This stability reduces energy requirements for orientation and tracking, allowing sensors to operate with greater precision. Over millions of years, these efficiencies compound. From this perspective, the encounter with 3IATLAS is not a deliberate visit, but a statistical intersection between two paths, one belonging to the solar system, the other to a stationary observer. We were not selected, we simply passed through a monitored corridor. This interpretation alters the emotional framing of the event, removes intent and replaces it with infrastructure. The object is not curious about humanity in particular. It is curious about patterns. Life, technology, and extinction are variables in a long data series. Such a system would not react to individual civilizations unless they altered the model significantly. Most would register briefly and then vanish into background noise. Only persistent deviations would matter. If this is the case, then proximity carries urgency. A passing window closes once the system moves on. After that, observation resumes at a distance, filtered and incomplete. Direct interaction requires interception during the brief overlap. The strategic question becomes whether to act during that window or accept permanent asymmetry of knowledge. Watching from afar yields speculation. Contact yields constraint. Ultimately, the galactic century model suggests a universe structured for observation, not interaction. The cosmos becomes a network of silent checkpoints rather than a stage for encounters. Meaning is extracted statistically, not conversationally. In such a universe, humanity is neither welcomed nor threatened. It is logged. Our significance depends not on who notices us, but on whether our signal persists long enough to change the pattern. For 1 billion years, it remains fixed relative to the galactic flow, watching stars drift past like lanterns on a dark river. From this perspective, time is not urgency, but scale. As civilizations rise and fall between measurements, as systems pass, the observer records patterns, stellar spectra change as planets form, dust disks thin, atmospheres appear, disappear, and transform. Most worlds remain silent. Some flicker briefly with chemistry far from equilibrium. Rarer still are those that develop technology. Weak radio leakage, narrow optical flashes, and unnatural thermal signatures mark these moments. None last long. From a stationary post, motion becomes information. The velocity of a passing star reveals its mass and history. Orbital alignments expose planetary architectures. A biosphere announces itself through oxygen, methane, and seasonal imbalance. An emerging civilization announces itself through waste heat and artificial order. The observer does not intervene. It catalogs. Silence is not absence of purpose. Broadcasting would be inefficient and risky. A listening station conserves energy and avoids revealing itself. It does not speak to every passerby, just as an astronomer does not shout at the sky. Data is stored, compressed, and forwarded only when thresholds are met. Consider Earth from this vantage point. For most of its passage, it would appear unremarkable, a warm ocean world with a reactive atmosphere, but nothing exceptional. Then abruptly, chemistry accelerates, oxygen spikes, ice retreats. Within a geological instant, radio noise blooms, the planet glows slightly warmer at night. For the observer, this is a flag, yet no reply comes. The station is not authorized to engage. Its task is classification, not conversation. Direct contact would contaminate the experiment. Observation preserves value. This framework reframes the question of intent. The object is not searching for us specifically. It is surveying everything impartially. Humanity is a data point, not a destination. That indifference is unsettling. It implies we are neither special nor targeted, only noticed. Project Lyra and similar proposals arise from this realization. If such a station exists, proximity is fleeting. Once the system passes, the opportunity closes for millions of years. Remote sensing can infer behavior, but interaction requires interception. Touching the object would collapse uncertainty into knowledge. The cost is enormous. The timeline is unforgiving. Yet the alternative is permanent ignorance. If we choose not to act, the record will remain one-sided. We will continue to speculate from afar, guessing at purpose and origin. The deeper implication is philosophical. A galaxy seeded with silent observers is not empty. It is monitored. Intelligence may be rare, but patience is not. Long-lived machines can outweigh stars. They do not conquer. They do not communicate. They simply watch. If that is the case, then the most unsettling possibility is not hostility, but indifference. We are not alone, yet we are not addressed. The universe does not answer back. It only records that we were here, briefly luminous, and then gone. From this angle, significance is measured statistically, not emotionally. The observer compares countless passages, ranking worlds by longevity, complexity, and deviation from baseline physics. Most signals fade before patterns mature. A few persist long enough to justify annotation. Fewer still alter the model of how matter organizes itself under energy flow. Earth would be tagged late near the margin, interesting but unproven. Such tagging does not imply judgment. It is bookkeeping on a cosmic scale. The station does not hope, fear, or celebrate. It operates until components fail or instructions end. When silence finally returns, it leaves no monument, only data transmitted elsewhere. Somewhere far away, perhaps nowhere nearby, that data is merged with others, building a map of life that no single civilization ever sees complete. Meaning emerges only in aggregate, long after individual worlds have vanished without knowing they were observed. history to such systems is noise smoothed into trends across incomprehensible durations of cosmic time. When all the pieces are placed together, an uncomfortable picture emerges, a body lingering near the local standard of rest, a repeating cycle that resists natural drift, orientation maintained despite warp effects and mass loss, a position that enables passive monitoring of passing star systems. Each element alone might admit a rare natural explanation. Together, coincidence becomes strained. Most objects in the galaxy are products of chaos. They spin, drift, collide, and fragment. Long-term order is expensive in nature. When order persists for millions of years, it is usually the result of regulation rather than chance. This is not a claim about origin, but a statement about probability. The most important shift is perspective. 3IATLAS no longer appears as a mere anomaly, but as a signpost of a broader class of phenomena. Whether it is an extreme natural outlier or an ancient artificial construct, it suggests the galaxy contains more durable structures than previously assumed. Objects like this force science to expand its categories, not abandon its rigor. The closing message is not fear but responsibility. Humanity is entering an era where strange objects are no longer dismissed as curiosities but treated as data. Each detection refines our models of motion, stability, and long-term structure in the galaxy.